Hi, in this video I'll demonstrate how to do electricity investigation 3. So first look at the instructions in list of FET electricity experiments. So in the third experiment it says set up circuit 2 in FET as shown in the circuit diagram. So let's look at the circuit diagram. So the second circuit diagram is this one. So let's understand it first. It has a battery which will provide the potential difference required to drive the current through the circuit, and then it's connected to a resistance, and you have an ammeter in series to measure the current flowing through it. Then you have another resistance, and then through a switch it is again connected back to the cell. So now you also have a voltmeter to measure the voltage or potential difference across this particular resistance. In other words, this ammeter will help you to measure the current flowing through this resistance, and this voltmeter will help you to measure the voltage across this resistance. Okay, so the idea is, by changing the value of this particular resistance, the total resistance in the circuit can be changed. So when the total resistance of the circuit is changed, the current in the circuit will also change, because you have the same fixed voltage, but now the total resistance in the circuit is changing, so the current in the circuit will also change. So the current which is passing through this fixed resistance will also change. And our research question is, how does the voltage across a fixed resistance vary when the current passing through it is changing? So that's the idea. That's why we need two resistors in this circuit. Clear? Okay. So now let's quickly make these connections. So we'll go to the FET simulation and we'll quickly add on the cell. So let's use the schematic system so that it will fit in a smaller space. So I have a cell, and then I have connecting wire. Okay, before I continue, my students who are sitting with me, they had again some confusion about why we need this other resistance here. So let me explain that point in more detail. See here, the goal of this experiment is to find out what effect current has on this resistance, in the sense that there is some potential difference across this resistance. How does that potential difference change if we change the current passing through this resistance? Now imagine that you don't have this first resistance, you have only this 10 ohm resistance and this battery. So then the current passing through this 10 ohm resistance is fixed. It is given by Ohm's law, I is equal to V by R. So V is 9 volt, R is 10 ohms. So the current is V by R, that is 9 by 10. So 0.9 amperes. So that is fixed. But our research question is, if we change the current, how will the potential difference vary? So if I don't have this first resistance, I can't even change the current. So how can I find out the answer to my research question? So I need a mechanism to change the current through this resistance. For that, I need to change the effective resistance of this whole circuit. So that's why I need one more resistance here. So by changing the value of this resistance, the total resistance will change, and so the total current in the circuit, which is given by the potential difference provided by the battery divided by total resistance, so the current will also change. So as I increase this resistance, the total current will decrease, because the total resistance is increasing. So I can see what is a new current I am producing using this ammeter, and for that new current I can measure the new voltage which is dropped across this using this voltmeter. So we know that by Ohm's law, potential difference across this resistance V will be I into R, where R is this fixed resistance and I is the changing current. I hope now it is clear.
Yes, sir.
Okay, so now let's quickly set up the circuit. So we already put the battery here, connecting wire. Let's add one more connecting wire here. Now we'll add one resistor and we'll add one ammeter. We'll add one more resistor. Okay, we'll add one connecting wire here. Then we'll add one more wire and we'll add one switch. Yeah, now we'll add the voltmeter also. Okay, we'll keep it below. So now the positive terminal of the voltmeter I should keep at the higher potential point. So the higher potential point will be starting out from the positive terminal of the cell. So this will be at highest potential and then some potential will decrease. So this will be the higher potential end of the resistance, the constant resistance. So let me put the positive terminal here and the negative terminal here at the lower potential point. So this end will be at 0 volts. So now we are all set. Let me close the switch and I can see that the current is flowing. So the circuit is functional. Now let's look at the observation table. So for that, let's go to the observation table for experiment 3. So as I said, the research question is, how does the potential difference across a given resistance vary with the current passing through it? So potential difference across the cell, I should fix it. So let me take some value. Let us take what?
Sir, you made an this circuit diagram is for experiment 2.
No.
Yeah, so you can check if you want.
See, this is experiment 3. You have to use the same circuit diagram as experiment 2. Okay? Clear? So let's pick a value for the, okay, first we need to pause it, then only we can change the values. So now right click on the cell and change voltage. Let's put 12 volts, the typical battery which we have in shops. And no, it automatically changed before I clicked it. So what you should do is type 12 and press tab so that it gets registered, then click on done. You can also say show value so that you are sure that is the value it has taken. So it says 12 volts and 0 ohms. That means the cell doesn't have any internal resistance, but real cells, they do have some internal resistance. This is just a theoretical circuit, so it's an ideal battery without any internal resistance. So now let's type it here. Since I use 12 volts, I'm typing it here 12 and I'll put the unit in the other cell, V. Now resistance of second resistance also I need to fix for the whole experiment. So let me put say 10 ohms. So right click, change resistance. It's already at 10 ohms, so let's keep it at that. You pick some other value for your experiment and I will do show value so that I'm sure it's exactly 10 ohms. So I'll type here 10. Now put the unit, go to insert, symbol and select ohms. Okay, now we need to vary the current, so this is our independent variable and potential difference across the second resistance is the dependent variable. So now I need to get some values of current which are equally spaced and cover a big range. So I need to know what resistance to put here. So I'll just do trial and error and see. So right now it is 0.45 amps. So let me see what is the default value of this resistance. Show value, it's 10 ohms. So let me see what happens if I put 1 ohms for that. Okay, if I put 1 ohms, it will give me the maximum current. So I want to increase the current from lowest to highest value. So let me start with some high resistance, say 20 ohms. So now it's 20 ohms and the current is 0.45 amps. Let me play the animation. Okay, if I play the animation, it's showing 0.4 amps. Okay, so I think if I now let me see if there is a significant change in the current if I change it from 20 to say 18. Tab, done. Now play. So it's 0.43, so there is not much significant change. So let me again change it to 15 and see. First I need to understand what should be the interval when I change the values of resistance, so that there is a significant change in current. The current values should not be too close together.
In the previous one, it came like 0.45 and 4.5, right? Here it's 4.2.
So now let me change it to 15 ohms and see what happens. So again the current is changing only in second decimal value. So let me make it 10 ohms and see what happens. Yeah, so now it's showing a significant change. From 0.4 it became 0.6. So from 20, 10. Okay, let's see what happens if we make it 30 ohms. So first you should play around with the simulation and see what happens. Then only you can finalize a suitable value of suitable range of independent variable values. So let's make it 30 and see what happens. Play. Yeah, it's changing. So for 40 I think it will go to 0.2. Let's check it. Yeah, so I think you can go up to 50, 60. So let's try 60 ohms. What happens? What happened? Yeah, 60. Tab, done. Click on play. Yeah, so up to 60 ohms. So we can start with the maximum of 60 ohms and keep on decreasing it. So that will be our plan. So let's type here. We'll start with 60, then we'll go on to 50, 40, 30, 20, 10, 5. So first let's take the values of current and voltage for these, and before that V2. So let's make it into a subscript. So select the two, format cells, subscript. Okay, so V2 is the potential difference across the second resistance whose value is 10 ohms. here also. Okay, so let's note down the measurement values. So first is 60 ohms. Right click, 60 ohms, it's already at 60 ohms. Play, and the current is 0.17 amperes. So note down 0.17, and the voltage is 1.71 volts. 1.71. Next, let's pause it, make it 50 ohms. Right click, change resistance, 50, tab, done. Now play. Current is 0.20 amperes. 0.20 amperes. Voltage is 2.00. Next, 40. So pause it, right click, change resistance, 4. So I completed the table by changing the values of resistance as shown here, and I noted the corresponding current values and the voltage values. So the next step is to plot the graph of the potential difference versus the current through the second resistance. So let's select all the data points. Now before we do that, we have to make the values of same number of precision, to have the same precision, that is the same number of decimal places. So let's select all the cells, right click, format cells, number, again number, 2 decimal places, because the ammeter was showing the reading up to 2 decimal places. Similarly, the voltmeter was also showing the readings up to 2 decimal places. So let's set it also to 2 decimal places. Format, number, 2 decimal places. Okay. Yeah. So now we can directly plot it. Insert, scatter, scatter. So this is the graph. Let's put the title, chart title, above chart. It is potential difference V versus current through resistance, or simply we'll say V versus I. And axis titles, horizontal axis title below axis, it would be current through second resistance I / amperes. And on y-axis, axis titles, primary vertical axis, rotated title, it would be potential difference across second resistance V2 in volts. Now the 2 we have to make it into a subscript, so select that, press shift and right arrow key or up arrow key, and then right click on that selected 2, go to font, select subscript. Okay, so now it's fine. So next we have to fit the straight line graph through these data points. So go to trend line, more trend line options, and by default it would have selected linear. So next thing is to extrapolate it so that we can show that it passes through the origin. So select backward, and it is around the x coordinate of the current is 0.17. So let's type that much value, backward 0.17. Click on the other cell, you see that it now passes through the origin. Then display equation on chart, display r squared value on chart. So you can see it's a perfect straight line graph. The r squared value is 1 and the y-intercept is practically 0 and the slope is supposed to give the resistance, and the resistance we used was 10 ohms and it is 10.003. So it's exactly verifying our Ohm's law. So that is what you will write in the conclusion. So I'll write the conclusion for you here. So conclusion can be, but you have to write it in a Word document in the form of a report. Okay. So conclusion would be the Ohm's law was verified since a plot of current versus voltage produced a linear graph and the slope here it's a plot of voltage versus current. Produced a linear graph and the slope gave the value of resistance to be 10.0 ohms. So you can insert the symbol which was used in the experiment. So I hope you understood. Y is equal to mx, so that exactly matches with V is equal to IR, where I is x, R is 10.003.